Welcome back, everyone. Okay, so now you're familiar with pure substances, which we call elements, which can be allotropic forms of the same element, or compounds. Now let's start talking about mixtures. Mixtures are by definition impure. They can be, as we'll see, homogeneous, heterogeneous, and they can be separated back into their pure components. So we're going to refer back frequently to this classification chart that can be found in the OpenStax chemistry textbook. Check the link description below if you want to access that as well. Now, when two or more substances are physically mixed together, they do not form new bonds between them, okay? So the mixture can be separated back into their pure components if it's desired, as we will see later. The key term here is physically mixed. So this is a physical process that can be reversed. It's not a chemical reaction. So the substances that were mixed remain distinct, all right? They don't react or change. In this image, we can see chocolate chips, right? In trail mix, that's a mixture of nuts and flakes and some other delicious looking things. Now, if we wanted to, we could pick out the chocolate chips to get that pure substance back again, okay? Now, a homogeneous mixture, on the other hand, appears uniform, but a heterogeneous mixture appears granular. All right, so let's talk more about what I just said. Homogeneous mixtures appear uniform. So we can be familiar with salt water, which looks just like water, right? And it's uniform throughout and doesn't need to be mixed up or shaken before using. And so this is because all parts of the homogeneous mixture are uniform throughout and contain the exact same quantities of water and salt, the primary substance used to create, salt water, right? And we're going to encounter solutions more in this class. Solutions, by definition, are homogeneous mixtures in water, okay? So here we have a slide showing a drip. It's an IV of a saline solution, which is salt water. So water is a chemical compound. Sodium chloride is a chemical compound. And when the two are mixed together, it looks just like water, but we call that aqueous sodium chloride, which is a solution, a homogeneous mixture. Another example of a homogeneous mixture is iced tea. This particular iced tea is Arizona mango orange iced tea. I think it's a green tea iced tea. Now, this particular iced tea is a very complicated mixture of green tea, natural orange, tangerine, jasmine, honey flavors, and like a ton of other stuff in there if you read the ingredients. So, of course, it's a mixture. Now, when you open this and pour it into a glass, it looks uniform throughout. You don't need to stir it or something like that, okay? So this is a perfect example of a homogeneous mixture. Now, we haven't talked a lot about chemistry yet, so I have to use common food items to discuss these things. So here we have a heterogeneous mixture. Now, heterogeneous mixtures have granularity, or parts and pieces, or they look chunky, okay? And those are readily visible just with our eyes, all right? So a T-bone steak is meat here before it's cooked is not uniform. It's made of gristle, fat, meat, so on. Bone, did I mention bone? Heterogeneous mixtures, again, have granularity or parts and pieces in them and that are readily visible, okay? This is just an ordinary photograph of a rock known as granite, and there are gray, white, and dark spots that you can see, okay? And if you've taken geology, you know that they're associated with quartz, feldspar, and mica, and each of these are comprised of complicated arrangements of atoms, extremely complicated. Most of the Earth is made of silicon, aluminum, and oxygen, the solid part of the Earth, okay? So you can see some of their chemical formulas there. They're just crazy looking, okay? But most of these formulas have silicon, oxygen, or aluminum. All right, let's talk about separation techniques. Now, distillation is a physical technique, or it's not a chemical reaction. It's a physical technique used to separate two components with very different boiling points. For example, salt does not boil at reasonable temperatures. It doesn't even evaporate, right? But water does. So if we heat up a mixture of salt water, pure water will come out and the steam can be condensed to form pure water. Okay, so for example, in a desalination plant. And then the solid salt that's left behind is a pure substance or a compound known as sodium chloride. Another example is ethanol. Okay, now this is a distillation apparatus. Okay, it's a still. Okay, now it works on the idea to separate ethanol and water. Now ethanol has a boiling point of about 78 degrees Celsius, but water has a higher boiling point of 100 degrees Celsius. So if we put a mixture on the lower left there containing water and ethanol, and we boil the mixture, the lower boiling point ethanol will boil off first and condense in that condenser tube, okay? And it'll collect onto the lower right, all right? And the purpose of using ice there is to, below the collection bulb, which you can't really see, is to prevent the ethanol from evaporating and, escaping. Obviously, that's what you want to obtain for whatever research purposes, of course. Separation techniques include distillation, as we've discussed, and filtration. Okay, filtration is also a physical technique used to separate two components, one being a solid and one being a solution or a liquid. And so, for example, we can all relate to making coffee. So these little brown papers here are filter papers that are used to separate the grounds from coffee, the coffee that you drink. Okay, so when hot water is poured onto the coffee grounds, it extracts color, flavor, and of course caffeine from the grounds. Okay, the water containing these chemicals is now a solution that easily passes through the pores of the filter paper. Okay, but the larger coffee grounds are retained by the filter paper, and so the liquid and liquid portions can be separated from one another. Okay, so it's like a size technique, a size separation technique. Here's a laboratory filtration that we might do in the lab. And so there's this little tubing there that connects the vacuum to the filtration flask there. And it's used to draw liquid through the funnel. Okay. Now we can see some liquid above the funnel there that's supported on the flask. And when the vacuum's turned on, any solids will be trapped by the filter that's visible here barely in the video with a white line or a disc there. Okay. So the solid will get trapped on that, but the solution or liquid will be able to pass through the filter into the filter flask below, so that you could separately analyze the solid that has stayed on top of the filter, or you could analyze the liquid or solution or whatever it is that passes through the filter into that Erlenmeyer flask down below. So again, we're going to refer back to this flow chart. Hopefully you have your OpenStax chemistry textbook at the ready here, and we'll give you a couple practice problems. But again, I'm not going to give you the answers here, okay? Practice problem number 1. Take a look at these chemical formulas, 1, 2, 3, 4, and answer the question, okay? Classify the following as elements or compounds. So which of these are elements? Which of these are compounds? Okay, pause the video, write your answers, see what you get. If you're taking my class, you'll want to put these into a sheet of paper and turn them in electronically. All right, so we've got some names and then we've got some chemical formulas. So that's your clue to decide if they are elements or compounds. All right, I hope I'm not going too fast for everybody. Here's practice problem 2. Take a look at these descriptions of food and decide what type of mixture is it. Is it heterogeneous or is it a homogeneous mixture? So you'll have to remember what the characteristics of those are. So we've got Rocky Road ice cream. If you don't know what this is, it's ice cream with marshmallows and with nuts in there, okay? Baby food, and I chose carrots. You remember what baby food looks like, I think, right? Or can imagine it. Vegetable soup, and we've got milk. Okay, this is not sour 10-day-old past expiration milk. This is fresh milk that you get from the store. All right, so answer that question. Once again, if you're taking my class, you'll want to turn this in. Practice problem 3. All right. So this is the most complicated type of question you will encounter that pulls everything together. So if you're studying my videos, this is as complicated as it gets. Look at the substances and decide for yourself how to classify that substance, okay? Remember, we have 4 categories: elements, compounds, homogeneous mixtures, and heterogeneous mixtures. If you're not sure, look at the flow chart and answer the yes or no questions to decide how you would want to classify these, okay? So we've got silver, all right? By the way, if you're not sure if one of these substances is on the periodic table, you can look for it, okay? The names will be all on here and you can try to find it. If it's a name of an element, there's only 118 of them, it's going to be on this periodic table. Mouthwash, iron filings and sand, and then water. Okay, so thank you very much for watching. Give a thumbs up. Please consider subscribing and have a great day, everybody.